This video will cover Chapter 8, Gases. The learning outcomes for the chapter will involve defining pressure and its units of measure and being able to convert between those units, and then describing how pressure, temperature, moles, and volume of a gas are all related to one another. Then we will perform calculations that involve these gas variables, and we'll use what's called the combined gas law and the ideal gas law. We'll then use the ideal gas law to calculate the density or the molar mass of a gas. We'll move on to mixtures of different gases, and we'll use Dalton's law of partial pressures to perform calculations on these mixtures. While the previous learning outcomes involved gas laws, and laws are mathematical summaries of observations, this next learning outcome will help to explain why those laws are observed. It's called the kinetic molecular theory of gases. We'll move on to kinetic energy, and we'll calculate the average kinetic energy of a gas sample based on its temperature. We'll then calculate the average velocity of a gas sample based on molar mass and temperature, and we'll compare velocities of different gases at the same temperature. We'll begin with the variable of pressure. Pressure is defined as the force applied to a surface. So it's force divided by area. And the SI units of pressure are derived from force having the SI unit of Newton, which is a capital N, and of course area having the SI unit of meters squared. We can then break down the Newton because the Newton is actually a kilogram meter per second squared. And so if we now combine that with the meter squared in the denominator, we end up with kilograms per second squared per meter. That is the unit of pressure, and we have a common name for that. It is called the Pascal, and the variable is PA. So I say all of this to tell you that in chemistry, we almost never use pascals. In chemistry, we typically use either atmospheres or millimeters of mercury, which is the same as torr. So how does that chemistry unit compare to the SI unit for pressure? Well, there's about 101,000 pascals in one atmosphere. And one atmosphere contains 760 millimeters of mercury, or torr. Sometimes you'll see the old English units for pressure. You might see inches of mercury, or you might see pounds per inches squared, PSI. And so we want to be able to interconvert between all of these different pressure units. So that's what we're going to look at to start with. Pressure is measured in a flask using a device called a manometer. It's measured in the atmosphere by using a barometer. And in the diagram below, we see that the manometers are on the left and the barometer is on the right. OWL 8.1 will give you a chance to practice interconverting between different pressure units. Okay, so we have a student reading a barometer for atmospheric pressure, and they take a reading of 717 millimeters of mercury. We want to express this in all of the different pressure units that we were just talking about. So firstly, we will convert that to atmospheres. Very simple conversion. We take the millimeters of mercury and we divide it by 760. You can see with the dimensional analysis that the millimeters of mercury cancel out and you're left with atmospheres. And this particular calculation will have three significant figures, so we end up with 0.943 atmospheres. We could do a similar type calculation and convert from millimeters of mercury to kilopascals, okay? And so 101.3 kilopascals is equivalent to 760 millimeters of mercury, and when we perform this calculation, we get 95.6 kilopascals. Of course, torr and millimeters of mercury are the same thing, and so you don't really have to show a calculation for that. We just know that they're the same. And then if we want to go to pounds per square inch, we would multiply by 14.69 psi over 760 millimeters of mercury. Lastly, we can convert to pascals following the same procedure, and we get 9.56 times 10 to the 4 pascals. Be sure that you're comfortable interconverting between the different units of pressure. And we'll move right into the gas laws. We'll be focusing on Boyle's law, Charles' law, Avogadro's law, and we'll also look at a couple of others. I want to start with Boyle's law. So take a minute, pause this video, and watch this 1.5-minute video that demonstrates Boyle's law. From the video, you'll see that pressure and volume are inversely proportional. That means that as pressure of a gas increases, its volume decreases. I like to think of that as a balloon. If I squeeze the outside of a balloon, it's going to get smaller, right? So high pressure, lower volume. Mathematically, we can represent this as the product of pressure and volume is equal to a constant, because as one goes up, the other goes down. If we had two sets of conditions, we would say, okay, since the product is always constant, the product of a pressure and volume under one set of conditions is going to be equal to the product of the product pressure and volume in a second set of conditions. P1V1 equals P2V2. For this calculation, you can have pressure in any units, and you can also have volume in any units. Boyle's law can be nicely represented with a graph. If we look at a plot of pressure versus volume, we see that as the volume increases, the pressure decreases, and vice versa. Next, we'll look at Charles' law. Take a minute and pause the video and watch the demonstration. So what you noticed from the demo was that temperature and volume are directly proportional. As you increase the temperature of a gas, its volume also increases. Mathematically, we would say, okay, if they're both increasing and decreasing together, then the ratio of those two numbers is going to be a constant. K represents a constant. If we have two sets of conditions, we would then say the ratio under condition set 1 is equal to the ratio under the second set of conditions. Now, for this calculation, you need to be aware that although volume can be in any units, temperature must be in Kelvin. For any gas law calculation, temperature must be in Kelvin. Now, I realize in the previous chapter 7, we talked about chemical energy, and when we did calorimetry calculations, we used temperature in degrees Celsius. So make sure in your mind that you keep that separate from gas law calculations where temperature needs to be in Kelvin. And the plot of volume and temperature shows a direct linear relationship. As temperature increases, volume also increases. And again, note that the temperature needs to be in Kelvin in order to observe this relationship. Next, we're going to look at Avogadro's law. Take a minute, pause the video, and watch the demonstration that is linked at the top. From the video, you'll see that Avogadro's law states that moles and volume of a gas are directly proportional. Mathematically, we would represent that as the ratio of moles and volume is a constant K. If we have one set of conditions and then a second set of conditions, the ratio of volume and moles will always be constant. For this equation, volume could be represented in any units, and N is moles, and it would obviously be expressed as moles. And the graph of volume versus moles is very similar to volume versus temperature. As the moles increases, so does the volume of the gas. They are directly proportional. Another way that Avogadro's law can be stated is that equal volumes of different gases will always contain the same number of moles, no matter what the identity of that gas is. And we know that 1 mole of any gas at standard temperature, 0 degrees Celsius, and pressure 1 atmosphere, occupies a volume of 22.4 liters. You may have been wondering why there's a picture of a man holding a beach ball on the slide. Well, a beach ball is about 22 liters in volume, and so that will contain 1 mole of gas. Of course, it's mostly filled with air, which is a mixture of nitrogen and oxygen. We can use this relationship when we are at standard temperature and pressure, STP, to interconvert between volume and moles. Another law that relates to the gases is called Guy-Lussac's law, and there's a demonstration of this law. Take a minute, pause the video, and watch the demo. Okay, so from the video you can see that temperature and pressure are directly proportional, and mathematically we would represent it very similar to how we represented the other direct relationships. The ratio of the two variables that are directly proportional is equal to a constant. If you have 2 or 3 sets of conditions, the ratios are always going to be the same. Since temperature is involved here, remember temperature for these calculations needs to be in Kelvin. Pressure can be in any units. It's not convenient to use the separate laws as separate equations, so we're going to have one equation that deals with Boyle's law, Charles' law, and Avogadro's, as well as Guy-Lussac's law, and it's called the combined gas law. We take all the variables that we were just discussing, and this is how they're all related. Oftentimes we are not dealing with moles, and so N for moles can be left out of the equation, and we would use the combined gas law like this. This is a very powerful equation to use when you're dealing with changing conditions or 2 sets of conditions. So let's say we have the first pressure, the first volume, the first temperature. We have the second temperature, the second pressure, but we don't have the second volume. We can use this equation to calculate that second volume. Now we're going to look at some examples. In AL 8.2, we're given a sample of oxygen gas at a pressure of 1.17 atmospheres and a temperature of 24.8 degrees Celsius. So a little bit of a red flag when I see degrees Celsius. I know that I am going to need to convert that to Kelvin. Okay, this gas occupies a certain volume, and that is 679 milliliters. If the gas is allowed to expand at constant temperature with decreasing pressure, what will the volume of the gas be? With these problems, I recommend that you summarize the data in a little chart on the left. So we have our initial pressure of 1.17 atmospheres, initial temperature that we do need to convert to Kelvin. We have our initial volume. The second temperature is the same. The second pressure is 0.851 atmospheres, and we are asked to calculate the second volume. So having all that there helps me to map out what I need to do. Since I have 2 sets of conditions, I'm going to use the combined gas law. And in the combined gas law, I'm not going to need to use the moles or the temperature. Both of those are constant. So it's really just going to be pressure and volume. So you can always knock out the variables that are not changing. Plug in the known variables and solve for the unknown, which is V2. V2 will be equal to 934 milliliters. The answer makes sense because I did decrease the pressure and the volume increased as expected according to Boyle's law. That's your reality check that you'll always want to do with these problems. Let's look at another one, AL 8.3. We have a sample of oxygen gas at a pressure of 1.06 atmospheres and a temperature of 256 degrees Celsius. Mental note, I need to change that to Kelvin. We also have a volume of 680 milliliters. The gas is being heated until its volume is 859 mils. We want to know what the temperature is going to be if I hold pressure constant. In summary, here is all of our data. We had pressure remaining the same, so we will be using the combined gas law, but we won't need moles or pressure. So it will simplify to V1 T2 equals V2 T1. plugging in the values from my table. A common mistake I'll let you know that students make is they might get the first volume and the second volume swapped, or the first temperature and the second temperature swapped. And that's where writing that little table of your summary data is going to be helpful to avoid those types of errors. So in this problem, we calculate our temperature to be 668 Kelvin. Note that OWL does want you to put the number back in as degrees Celsius. So how am I going to convert that? I'm going to subtract 275.15 to get my temperature in degrees Celsius. Now we're going to look at OWL 8.4. Which of the following gas samples would have the largest volume if all samples are at the same temperature and pressure? So which would have the largest volume? And so we're given grams, we're given moles, we're given molecules. It would be useful here to convert everything to moles. And the one with the largest volume is going to have the greatest number of moles according to Avogadro's law. So let's go ahead and convert them all to moles so that we have an apples to apples comparison. For the first sample, we need to divide by molar mass. We look on the periodic table. Neon's molar mass is 20.18 grams per mole. So dividing the 40.4 by 20.18 gives us 2 moles of neon. The second one is already in moles, so we don't need to convert it. The third one, however, is in molecules. How do we convert from molecules to moles? For that, we're going to use Avogadro's number, and we're going to divide by Avogadro's number, and that will give us 0.664 moles of hydrogen. Now that we have gone and put all of them into moles, we can now make a good comparison. Which of these would have the largest volume? The one with the largest moles, and that would be 3.01 moles of methane. OWL 8.5, a sample of oxygen gas occupies a volume of 7.58 liters at 58.0 degrees Celsius and 0.890 atmospheres. All of those numbers, just pointing out, do have 3 significant figures. Okay, if it's desired to increase the volume to 9.88 liters while increasing the pressure to 1.08 atmospheres, what would the temperature of this new volume and pressure need to be? And again, they're wanting it in degrees Celsius, but to do the calculation, we have to convert to Kelvin and then back to Celsius at the end. Here's our summary data, a combined gas law problem because we're dealing with 2 sets of conditions. And do we need all these variables? We need all of them except moles, so we're going to simplify the combined gas law to this. And plug everything in from your table, solve for the second temperature, T2, and we get 524 Kelvin. Does the answer make sense? Well, the volume increased, the temperature should also increase, the pressure increased, and so did the temperature. All right, so we are going to have to subtract, as I said before, the 273.15 in order to convert it to Celsius, and when we do that, we will get the answer. So the previous calculations dealt with a system where you had 2 sets of conditions, and it used the combined gas law. Now we're going to look at a system where you're just dealing with 1 set of conditions, but we know 3 of the 4 gas variables, and we want to calculate that 4th unknown. For that, we're going to use the ideal gas law. The ideal gas law equation is very simple. It is PV equals nRT. R is a new one. What is R? R is what we call the ideal gas law constant, and it has a constant value of 0.08206 liters atmospheres per Kelvin mole. It's essential when you're working with this equation that you do plug all your units in so that you can make sure you set up your calculation correctly and everything cancels out to the desired units. OWL 8.6. We have 1.08 moles of helium. It's at a temperature of 13.0 degrees Celsius, and it occupies a volume of 23.6 liters. We want to calculate the pressure of the sample. You can see just from the wording, we only have one number of moles, one temperature, one volume, and we're asked to calculate one pressure. There's only one set of conditions, therefore I know that I need to use the ideal gas law. PV equals nRT. Okay, a couple of housekeeping notes. Because your R value is in liters times atmospheres per Kelvin mole, that tells me that my volume needs to be in liters. Of course, my moles are in moles. My temperature, as always with gas equations, needs to be in Kelvin, but my pressure in terms of the calculation is going to come out in atmospheres. So at the very end, I will need to convert those atmospheres to millimeters of mercury. Let's plug in our data. First, we're going to rearrange and solve for pressure. Plug in our data. And like I said, it's imperative that you do include all the units in your calculation. And then you can see, okay, the moles cancel out. The liters cancel out. The Kelvin cancel out. My answer will be in atmospheres. So when I multiply the numerator, divide the denominator, I get 1.075 atmospheres. That is an extra significant figure because I know I'm going to now have to convert atmospheres to millimeters of mercury. How do I do that? Multiply by 760 millimeters of mercury per 1 atmosphere. The atmospheres cancel out, and you're left with millimeters of mercury, which is 817 millimeters of mercury. Next, we're going to combine stoichiometry, which we've studied in chapters 5 and 6, with reactions that involve gases. Okay, so first of all, remember when you're balancing your equation, the coefficients of the balanced equation equate to the number of moles or the mole ratio between reactants and products. Well, for a reaction that involves all gases, those coefficients will also line up with volumes. That's because, remember Avogadro's law said that equal numbers of moles of different gases occupy the same volume, or you could say equal volumes of different gases contain the same number of moles. Therefore, those numbers could represent moles. They could also represent volume in liters or milliliters. We're going to look at a problem that illustrates that principle. OWL 8.7. What volume of butane, C4H10, is required to produce 76 liters of water according to the following reaction? So we have butane reacting with oxygen to form carbon dioxide and water. We need the balanced chemical equation, and so a little tricky to balance this one. The coefficients end up being 2, 13, 8, and 10. Those coefficients represent mole ratios, and they also represent volume ratios. So now we're going to put in the data that was given. We were told that 76 liters of water are produced, and we wanted to calculate the volume of butane. So I'll put question mark liters under butane, 76 liters under the water. Now I can go about doing my calculation. You're always going to start when you're doing stoichiometry with the known or the given, and that is the water in this case. And then you're going to convert from one to the other. So we're trying to go from water to butane, and we want the volume of butane. So we would say from those coefficients that 2 liters of butane react to form 10 liters of water. So we multiply by 2 over 10. We see that the liters of water cancel out, and we calculate a value of 15.2 liters of butane. So you'll know that you can just simply use the coefficients to go between volume of a reactant and product. You'll know you can do that when your reaction involves all gases. Let's see how we can use the ideal gas law to calculate other things besides pressure, volume, temperature, and moles. And so in this slide, we're going to look at how the ideal gas law can be used to calculate molar mass. We're going to substitute mass in grams divided by molar mass in grams per mole for moles, because as you can imagine, grams divided by grams per mole is the same as moles. So we can replace N, moles, for M over MM, and they're the same thing. We can then see that we have pressure on one side, we can put volume in the denominator of the right side, and we will now have m over v, which is the same as density. We know that density is equal to mass over volume. So I could take that m over v and just replace it with the letter d for density, and we now have an equation that allows us to calculate density or use density to calculate one of the other variables. So these are a couple of different variations of the ideal gas law. This top one, if we want mass and molar mass, the bottom one, if we want density and molar mass in that equation. So if you're dealing with a gas and you see that they are asking about density or molar mass, you know you need to use one of those other versions of the ideal gas law that I just showed you. So in this case, we are asked to calculate the density of chlorine gas. We're given its pressure and we're given its temperature. So this is one of those problems where it doesn't look like you're given a whole lot of information. However, if you recall, you can determine the molar mass because you know that it's chlorine gas. So how do I get the molar mass of chlorine gas? Well, going back all the way to chapter 1, we learned that there are 7 diatomic elements and chlorine is one of them. And so the molar mass of chlorine is 2 times the atomic mass of a chlorine atom, and it turns out to be 70.90 grams per mole. So we use our equation P equals dRT over mm. Why did we pick that equation? It has density and molar mass in it. We rearrange and solve for density, plug everything in, and watch as the units cancel out. That's a verification that we did set up the calculation correctly, and our answer will be in the desired units, grams per liter. So multiplying the numbers on the top, dividing the numbers on the bottom gives us a density of 2.30 grams per liter. The next section of our study on gases now deals with mixtures of gases. And there's a law called Dalton's law of partial pressures. And again, laws are summaries of what we observe. Dalton's law of partial pressure states that for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. So as you add more gases into the mixture, the pressure is going to keep increasing and they are additive. Mathematically, it's pretty simple. The total pressure is equal to the sum of the individual pressures of the individual gases in the mixture. So you might be thinking, yes, that's very intuitive. What do I need that for? Well, we could also integrate the other variables, the volume, the temperature, the moles, from the ideal gas law. We can substitute nRT over V for each of the pressures. And now, we have a way of getting some more information about these individual gases. Notice that if you think back to your algebra, we could factor out some of the variables that are showing up in each term. And those variables are RT over V. Because we're in a gas mixture, the temperature, the volume are the same for every single gas. So we factor that out. And now we see that the total pressure is equal to RT over V times the sum of the moles of each gas. And so as long as we know the moles of the gases in the mixture, we can calculate the total pressure of that gas mixture. In this problem, we're given a mixture of 2 gases, helium and carbon dioxide. They're contained in a 7.08 liter flask at 69 degrees Celsius, and we have the amount of each gas in grams. Of course, if we have grams, we can convert that to moles, right? We have 1.04 grams of helium, 9.23 grams of carbon dioxide. We want to calculate the partial pressure of carbon dioxide, and then we want to calculate the total pressure in the flask. So in summary, here is all of the information we have. Make sure that you convert your temperature to Kelvin when you're dealing with gases. Since we had grams, we needed to find the molar mass of each gas, and I've done that here. Carbon dioxide's molar mass, 44.01. Helium's molar mass, it's not diatomic, it's just a monoatomic atom. Its molar mass is 4.00 grams per mole. And we can go ahead and use the mass and the molar mass together to calculate the moles of each gas, which I've done here. So first, we are asked for the pressure of carbon dioxide. So I'm going to plug this into the ideal gas law. I have all of these values. I plug them in, and I can see that my pressure will be 0.832 atmospheres. And that's just the pressure of the carbon dioxide. In order to get the total pressure, I can use my Dalton's law of partial pressures equation, which will be simpler than the calculation that I just did. And so what I'm going to do is plug in RT over V. I have the moles gas, so I'll plug those in, and I'll get my P total, which is 1.86 atmospheres. So look very closely at the information you're given, what you're trying to find, and then map out the way that you're going to go about that calculation. Also, remember, when you're dealing with gases, you're going to need to be aware of your 7 diatomic gases, and there's a little acronym for that called Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Mole fraction is the ratio of moles of one gas to the total moles of gases in a mixture. It has the variable capital X, and it is a unitless quantity. To calculate it, you would take moles of the one substance divided by the total moles of everything in the mixture. And this mole fraction is proportional to the partial pressure of gas in the mixture divided by the total pressure of the mixture. And so we can calculate it either from the mole ratio or from the pressure ratio. If we had a mixture of helium and carbon dioxide gases at a certain total pressure and we knew the grams of each gas, could we calculate the partial pressure of each gas in the mixture? Notice in this problem we don't have temperature. We also do not have volume. So I want to show you a way that you can use mole fraction to go about doing this calculation. So for mole fraction, we're obviously going to need to convert each of the masses to moles, and I've shown you how to do that on the previous problem. Now that I have the moles of each gas, I can calculate the mole fraction. Mole fraction would be the moles of helium divided by the total moles, the sum of the moles of each gas in the mixture. Okay, so knowing that the mole fraction is equal to the pressure ratio, we can use this to actually calculate the pressure of one of the gases. So knowing the mole fraction of each gas is going to very easily allow me to calculate the pressure of that gas. Just take the mole fraction and multiply it by the total pressure. You can do the same thing for helium that we did for carbon dioxide. And I have color-coded these so you can see which data goes with which calculation. To make sure that you did your calculations correctly, what I recommend doing is adding your total pressures together and make sure they add up to what your total pressure was originally. And in this case, we get 942, which was our total pressure. We can use Dalton's law of partial pressures in laboratory experiments where we are collecting a gas over water. What do I mean by that? Well, sometimes you have a gas that's formed in a chemical reaction. We're going to connect the flask to tubing, and we're going to have the tubing come up under a trough of water and go into, say, an upside-down graduated cylinder for collection. And so the gas is being bubbled through water, and it's getting saturated with water vapor in this process. So when you measure the total pressure with, say, a barometer, that total pressure is the sum of the pressure of the gas, P sub A, and the pressure of the water vapor that is entrained or mixed with that gas. What we are interested in, though, is just the pressure of the gas that we collected, and we would calculate it by taking the total pressure and subtracting the known vapor pressure of water at the temperature at which you're doing the collection. Here is an illustration of how that experiment would work, how the gas, oxygen, is being produced in the test tube, and then it's being collected in this upside-down container that is in a trough of water. In OWL 8.11, we have calcium carbide reacting with water to produce acetylene gas, C2H2 gas. This product is collected over water, so the pressure that we measure, the 748 millimeters of mercury, is the total pressure. We will need to separate and calculate the pressure of the acetylene gas. And the way we're going to do that is we're going to take the total pressure, the vapor pressure of water at that temperature, and subtract them from one another. And that will give us the pressure of the gas that we're collecting, which will be lower than the total pressure. We also look at the unknown variable. In this case, we want to calculate the grams or the mass of this gas that we're collecting. Since we know the formula, we can calculate the molar mass of the gas. We're given the volume, we're given the temperature in Celsius, and we do need to convert it to Kelvin. R, of course, is our ideal gas law constant, and we already have that. So I'll go ahead and convert my pressure to atmospheres, and then use the form of the equation that has mass and molar mass in it, and solve for mass. That's what we're looking for. At this point, it's an easy plugging in values into an equation. So we knew that we needed this version of the ideal gas law because we were calculating the mass, the number of grams of gas. And so it is this form of the equation that has mass in it. We also knew that that was the right equation because all of the other variables were given, and so we could easily rearrange and solve for mass. Make sure that you include your units in your calculation so that you can see everything cancel out except for the desired units. And that will help to ensure that you set these problems up correctly. So we've finally gotten to a point in the chapter where we have a theory that will explain these observed behaviors, these laws, these gas laws that we've been observing. The kinetic molecular theory of gases explains Charles' law, Boyle's law, Avogadro's law, the ideal gas law, all of them. And so we have four basic postulates to this theory. The first one is gases are comprised of tiny particles. Their size is negligible relative to the space between them. These gas particles are in constant random motion. They collide with each other and with the container walls. The collisions are elastic, that is, no energy is lost or gained when they hit each other. And the average kinetic energy of the particles is roughly proportional and directly proportional to the temperature in Kelvin. So let's use the kinetic molecular theory to make some predictions. We have two samples of gas, A and B. They both contain 10 molecules, therefore they have equal moles. We're told that the box on the right does have a larger volume than the box on the left. And we want to see if any of these statements are true. So first of all, are they both at the same temperature? No, they're not. If they were, they would have the same volume. Temperature will affect volume. Between box A and box B, which one has the higher temperature? Definitely going to be box B because we have a higher volume in box B, so therefore the sample in box B has the higher temperature. Since the particles in a gas sample are in constant motion, they have kinetic energy. And the average kinetic energy of a gas is directly proportional to its absolute temperature or Kelvin temperature. As temperature increases, so does the kinetic energy. The gas particles that are in random motion have a velocity. A velocity is a speed with a direction to it. And the relationship between this velocity and the molecular weight and temperature are expressed in this equation. So the root mean square velocity, which is kind of an average velocity, is equal to the square root of 3 times R, the ideal gas constant, times temperature divided by molar mass. We can see from this equation that the velocity will increase as temperature increases, and it will increase as molar mass decreases. The smaller the molecule or atom of gas, the faster it moves. Now we're going to look at an example using the equation I just showed you to calculate the root mean square velocity of gas molecules at a certain temperature. So it looks like we don't have very much information, but we can get the information we need. First of all, we need the molar mass. Oxygen is diatomic, so we will calculate the molar mass by adding two oxygens together, and we get 32 grams per mole. R is a constant, but please note that you're going to need to use this version of R. 8.3145 kilograms meter squared per second squared per Kelvin per mole. The units are going to be imperative for the R value, and the units for R will tell you that molar mass can't be in grams per mole. Instead, it needs to be in kilograms per mole. So we write out our equation, we plug in the values in the proper units, and let's look and make sure that the units will end up correctly. We're calculating a velocity. Velocity needs to be in meters per second. So everything else needs to cancel out. Let's see if that's going to happen. Kilograms cancel out with kilograms. Moles cancel out with moles. Kelvin on the top cancels with Kelvin on the bottom. I am left with meters squared per second squared. Well, you're going to be taking the square root of those numbers, and the unit will also get square rooted. So meters squared per second squared, when you take the square root of it, it will become meters per second. So the problem is set up correctly. And what we do is we put all the numbers together under the square root, then we take the square root, and we get 539 meters per second. That's usually the ballpark of where these root mean square velocities will be, somewhere between a couple hundred and 1,000 meters per second. When you think about it, a meter is roughly the size of a yardstick. That's quite a distance that a gas molecule is traveling in 1 second. The last topic we're going to look at is effusion and diffusion, and we're going to use the equation I just showed you to calculate the rates of effusion for different gases. First of all, we need to make sure we understand the terms. Diffusion is represented in this diagram. You can see your molecules on the left are at a high concentration, on the right they're at a low concentration. That is the natural order of things. Molecules will always move from high to low concentration. What is effusion then? Effusion involves a membrane with small holes in it, like you see in the diagram on the bottom. So it is a diffusive movement, but it's moving through a small hole. And you can look at demonstrations of each of these phenomena in the linked videos. So Graham's law of effusion states that the relative rates of effusion of two gases at the same temperature and pressure are given by the inverse ratio of the square roots of the masses of the particles. That sounds very complicated. Mathematically, it's a lot simpler. The ratio of the root mean square velocity of the first gas divided by the second gas is equal to the inverse square root molar mass of the second gas over the molar mass of the first gas. And you can see how from the original root mean square velocity equation, velocity is still inversely proportional to molar mass. In other words, the smaller the molar mass, the higher the velocity. Let's look at an example. We have in OWL 8.14, the average molecular speed in a sample of hydrogen gas. It just says certain temperature, so that's a clue that we don't need the full equation, we need the ratio. Also, we're going to see a second gas, another clue that we need the ratio. So we have the speed of the first gas, we want to calculate the speed of the second gas. We can calculate also the molar masses that will be used for this. It's imperative that you know that hydrogen is diatomic, but helium is not. And so there are the molar masses. Plugging everything into the equation, we can rearrange and solve for the average speed of the helium gas, and we get 324 meters per second. We now need to look and see if our calculated value makes sense. Well, the helium had a larger molar mass than the hydrogen, so we would expect it to have a slower velocity. And yes, it did have a slower velocity, so that result did make sense. So this is the last topic that we're going to cover. There's an optional topic at the end of the chapter, which is using van der Waals equation to calculate pressure, volume, moles, temperature for non-ideal gases. We call them real gases. It's a complicated equation, but it's not terribly difficult to work through. And you're welcome to do that as an optional exercise, and it will be an extra credit problem on the test. As always, if you have any questions, feel free to reach out. Thank you.